an SD, where the noise, in the limit where the noise is small, but we were thinking like that the drift term, for instance, we should keep as a reference the case where B is the gradient of some function, and this function looks like some limiting function perturbed with some little traps. And we were asking the questions whether or not, when beta goes to infinity, the process gets trapped in the traps or converges to the actual gradient flow of the limiting potential. Okay. We had just said that this is the process whose generator is just Ito formula, is 1 over beta the Laplacian plus the drift. If we call mu t the law of xt and jt the current of xt, then we always have, we gave it like the law of xt is clear for everybody. We made a very short kind of introduction to what this current means, but basically we checked that mu and j, they satisfy a continuity equation. The dt mu is the divergence of j. If we write it in a weak form, this means that dt mu integrated against any f is j integrated or acting on df. Okay, that's just the continuity equation. So for this reason, we introduced the space of all mu and j. So at the blackboard, I tried to make it more visible, like mu with the underlined mu, underlined j. This means that they are functions of time. Okay, so mu underlined means that for every t you have mu t as a probability, and j underlined means that j underlined t for every t is a current actually. So these are just the functions of time. Okay, mu and j, functions of time that satisfy a continuity equation. Okay. And then Kolmogorov equation, what is Kolmogorov equation? No, is dt mu of f is mu of Lf, right? L beta f, for every f. That's the weak formulation of the Kolmogorov equation, okay, where Lf is this guy. So we kind of lifted, we can lift this equation to currents. So instead of saying that dt mu is mu L, and dt mu of f is mu of Lf, we just say that the pair mu j is in the space U, is in the space of pairs that satisfies a continuity equation, and just that they are related by this condition. The jt is this special current that's like the typical j mu t, where I will j mu is given mu, j mu is one special current, which I call the typical current. So if you give me any measure mu, who is j mu of omega, is this guy, mu of 1 over beta, like this star of omega, like the divergence of omega, plus the scalar product between b and omega integrated in the mu. Okay, we have checked, I think, last time that it's immediate that this j mu of df, this is just mu of L beta f. Just because the Laplacian is this star d for functions. So you see that this equation, what does it mean? It means that jt of omega is j mu t of omega for every omega. So if you check the case where omega is exact, okay, jt of df is j mu t of df. So this implies in particular, yes, that jt of df is j mu t of df, which is nothing but mu t of Lf. So when you check our equation, this is our equation. When you check it on exact forms, you get Kolmogorov equation. So that's why I call it a lift of the Kolmogorov equation. Okay, it's a stronger. This statement is a stronger statement than Kolmogorov equation, because when you just look at it on exact forms, that's Kolmogorov equation. Okay, and then the idea. What was our idea? Instead of say that jt is equal to j mu t, what we say is that we introduce this. Let's go. Okay, this quantity. We have introduced this norm on currents. So if you have a measure mu, we have defined the norm on currents j in this way: the sup over all the omegas of j of omega minus the L2 norm of the one form. So that's like the L2 norm of the current. Okay. So who is so actually what does it? Okay. So what does it mean? This, why I call the L2 norm of the current? Because if, actually, and only if, j of omega writes as mu of E omega. So let's write it. If the current J is such that there exists E of X, a vector field, such that J of omega is mu, so it's really an integral current of E omega for every omega, then the norm, then J mu square is exactly the integral in the mu of E square. Okay? And actually only if the norm will have finite, a current will have finite norm, if and only if this E is in L2. So if you need actually to be a distribution. There is a Radon-Nikodym theorem for currents. Okay, that's just Radon-Nikodym theorem for currents. E is like the density of J with respect to mu. Just since J is a vector of distribution, the density is a vector field, not a function. So you see, I call it L2 norm of J, but you kind of have to divide J by mu, then take the L2 norm and integrate it in the mu, okay? Just because it's the dual norm of the L2 norm on the omegas. So, okay, and then so instead of, so that's, if you remember this trick that we made the first day for gradient flows, instead, we want to repeat it. So instead of writing, that's like a Lagrange, okay, instead of writing Jt equal to J mu t, so for almost every t or for every t, we write this lift of the Kolmogorov equation, Fokker-Planck equation, we write it as At of mu j, which by definition is like 1/2 the integral between 0 and t of j minus j mu t squared. I look at it in a moment, sorry. So this is by definition, this is less or equal than 0. So instead of saying, look, j is j mu t, okay, I define, I write it an equivalent statement that the integral in d mu t of jt minus j mu t squared, this norm squared, is 0. Since it's certainly positive, I say is less or equal than 0. Okay. Why? Because the very first day I showed you in some very simple example that writing some cases equalities as inequalities can be useful. Okay. So you should be careful because actually j mu t may not in general be a finite norm, but j minus j mu t will have. Okay. Then in reality it does, and I will be a bit sloppy on this. On this part. So, okay. Then let's us introduce very quickly the invariant. So the definition: m beta is invariant. So m beta. Sorry. Let's say it's a. I think we took some compact space. It's a probability on our space is invariant for L beta if m beta of L beta f is 0 for every f. Yeah, so this means that if you start this SDE at time 0 with this law, randomly with distribution m beta, at every time t will have the same distribution m beta, just because dt m beta will be 0. Okay. Now, it's a standard fact that since the noise is non-degenerate here, or in general satisfies some, this is true even for some degenerate noise, provided some assumptions are true, is that m beta as density, smooth density with respect to the volume measure. Volume measure you can think is like dx. Okay, the invariant measure is the density with respect to dx, which is a smooth, strictly positive everywhere. That's just the ergodicity of that process. And so I call it e to the minus beta v beta. Who is v beta? So v beta, by definition, is just 1 minus 1 over beta, the log of dm beta over dx. Okay? So since this density is smooth, strictly positive, it's well defined. Okay? And so what property does m beta have? It's just an integration by part, that if you do m beta of 1 over beta d star omega minus the gradient of this v beta omega, okay, that just means you can do the integration by part easily, integral in the volume of 1 over beta e to the minus beta v d star omega minus gradient v b omega. If you remember how this star was defined, it's just that exactly by the integration by parts. So the minus of the integration by parts with the minus here, they kill each other, and that's just 0. Okay, if you just do the integrate by part this divergence. Okay, so you see these, if you call R beta B beta plus the gradient of V beta, okay, you have that J. We can write that J mu, which is there, J mu beta. We can write it as S mu beta plus R mu beta. So where S mu beta at omega is just let me write it, then I comment on it, is mu of 1 over beta d star omega minus gradient v beta omega. And R mu of omega beta is just mu of R beta omega. So that's just, you check the formula for J, and you put these two together. Minus gradient V plus R is exactly B. Okay? So that's a trivial decomposition. Just let me remark that S m beta of omega, so if the measure here is really the invariant measure, is 0. And on the other end, R m beta. This fact is just this computation. And R m, so when the reference measure here is m of df, not over every omega, but just of the exact forms, this is J mu, so this is J mu m beta, beta of df minus S m beta, beta of df. So that's just m beta of LF minus 0, and that's at 0. Okay. So when I define here two currents. Okay, two currents. If the measure here in the index is exactly the invariant measure, the first one is exactly 0, and the second one is 0 on exact forms. Okay. The second one is, so this just tells me that since m is invariant, m beta of R beta df is 0 for every f. What I'm doing, I'm decomposing the drift. I'm decomposing the drift in two terms, one which is a gradient and one which is what remains. Okay. Just I do it in such a way that what remains is automatically orthogonal to exact form is L2 of m. You can do this in, I mean, we did it for every, it's just the existence of the invariant measure that tells us this fact. We derived it just from the fact that m is invariant. Is it okay? Very well. So now what let me think. So more in general, I think so. Let's do another remark. If mu has some density with respect to this invariant measure, then S mu of omega is nothing but minus 1 over beta m of d rho omega, which means minus 1 over beta mu of d rho over rho omega. That's probably should write gradient. Okay, so the proof proof is the same as here, just instead of integrating 1 by parts so that I get a 0, here there is a row. Okay, so maybe mu, so S mu of omega is just by the definition integral of e to the minus beta v beta rho. That's the definition of this rho, and then there is 1 over beta d star omega minus gradient v omega. So you just, that's by the definition of S mu beta. You integrate by parts and you get this formula. Okay. And another remark, which is that recall, so we have this norm, okay, defined up there. So let's this be the associated scalar product, okay? So that the norm is just jj mu, okay? So so if j prime of omega is equal to j, as a bit before, is equal to mu of e omega. So if a current j prime has a density with respect to mu with vector field E, then the scalar product of j prime is just j of, well, the one form AE. A was, you remember, was the square of the coefficients in front of the noise. It's the metric of our manifold. When I write there w dot, in reality there is a function, or a tensor that depends on x in front. Okay, so you can think this is the identity, yeah, if you want. Where does this remark comes from? Just a polarization. You know, if you want to write the scalar product of j prime, this is the norm of j squared of j plus j prime square minus the norm of j minus j prime square, and so. So it's enough to check it. It's actually by polarization. This statement is exactly. I should have remarked it here before. Probably, sorry. That's just j of AE. If j had this form. So once it's true on the squares, once the statement is true for the norms, by polarization is true for any scalar product. Okay. So this is just a simple writing. And so let's write the first kind of proposition. Or maybe we want first to recall. I already wrote these functionals, but since it was several days ago, maybe we want to recall that the relative entropy of one measure with respect to another measure was the sup of a roll function of the integral f in the mu minus the log of the integral v to the f in the m. And this was equal to the integral of rho log rho in the m if mu is rho m. Okay. And then we have I of, let's call it mu given m. Okay. For any measures. This will be, that is the integral of gradient of rho squared divided by rho. Do I need a half? No. In the m. Okay. If the same. So this is defined on any space. Okay. This I need a gradient and so on. I'm being slightly sloppy. I mean plus infinity when these objects don't exist. Okay, you can write, okay, this is very precise as a sup. One can do the same here, so I will not write it now. But okay, so let's call h beta of mu. Now these are just for any pair of probabilities. Now we have an invariant measure as a reference measure, and we have a parameter beta. So let's make call h beta of mu 1 over beta, the relative entropy of mu with respect to m beta. So it's like, okay, I think of it as h. So h beta is a function that takes a probability measure and give me a number in 0 infinity, infinity included. And the same I do for I beta of mu. That's 1 over beta square, I of mu given m beta. Okay, they both are functions from the space of probability to 0 infinity. And now I claim, so again, I'll be slightly sloppy here. suppose let's say proposition. Suppose that h beta of mu at time 0 is finite. Then I erase this sort of action functional of curves of mu and j, okay, which was by definition 1/2 the integral between 0 and t of j minus jt minus j mu t square mu t dt. This writes as h beta of, so here there was a beta, h beta of mu at the final time minus h beta of mu at time 0 plus 1/2 the integral between 0 and t of I beta of mu t dt plus 1/2 the integral between 0 and t of actually the same norm but with air. Okay. So the proof of this statement, yeah, I'm being slightly sloppy here because that's kind of Hilbert norm to say that the norm of the square is the sum of the square of the norm and so on. You need that both elements have to be in the Hilbert space. But I will be slightly sloppy on this question. So let me just write it like this. Jt minus this j mu t square, right? I just developed the square. So this is jt minus r mu t square mu t. Oh, this, sorry, let's not forget that this was s mu t plus r mu t, which are written down there. So that's this guy plus s mu t squared mu t plus the double product. So it's minus 2 jt minus r mu t s mu t. Okay, I just say that a plus b squared is a squared plus b squared plus twice the double product, and I hope the signs are correct. So then we are going to integrate it in time, divide by 1/2. Okay, so this guy is already here. We are happy. This was like the derivative, or the role of x dot square, if you remember the gradient flow formulation. So let's check that s mu t squared, so s mu mu, okay. Who is this guy? Well, as mu was 1 minus 1 over beta mu of gradient rho over rho omega, right? And I just erased it, but so okay. So this is, let me write it. This is the norm mu squared of the current mu minus 1 over beta grad rho over rho, like as a function of omega. Okay. So we have seen that when the current is mu, some vector field applied on omega, that's just the L2 norm of the vector field in L2 of mu. So this is nothing but the integral in the mu of minus 1 over beta grad rho over rho all squared. So this is exactly integral in the mu of rho 1 over beta square rho gradient rho square over rho squared. So that's exactly what we call the I beta of mu. I'm assuming that rho is regular enough to make this computation. Okay. So we are also very happy because that's the other part of the equality. So this guy is here. Then this guy is here. The 1/2 was in the definition. And then what else should I check? Well, let's compute the scalar product between R mu t, R mu and S mu. I claim that they are orthogonal, indeed, in mu. So scalar product with respect to the norm, always. So the scalar product induces this norm J square. So this is, by this fact, okay, if one of the two currents, I can write it as a density E with respect to mu, okay? That's just the other current applied to the vector field of which it was the density. So S mu as density minus 1 over beta grad rho over rho with respect to mu. What I just used there. So this is R mu applied to minus 1 over beta gradient of rho divided by rho. So to be precise. And that's, by definition of F mu, if you remember, was mu applied to the vector field R beta. R beta was how much was what remained when you remove from B this gradient part, okay? B, yeah, maybe I can write it somewhere like here. B beta was minus the gradient of V beta. This came from the invariant measure plus, okay, whatever remains. D rho over rho, minus M beta. Okay. So this is M beta of R beta d rho, minus 1 over beta d rho. And we have just remarked here that M of R applied to some differential is 0. So they are orthogonal in this L2. So the scalar product here is 0. And then we're just left with J scalar product with S mu. So this we should write it integrated. And that's JT against S mu t, scalar product with respect to mu t dt. That's the integral between 0 and t of always the same thing as here. I have a current. This guy has a density, as mu as a density with respect to mu. So this is JT applied to minus 1 over beta d rho over rho. Everything depends on t dt. So this is the integral between 0 and t. Okay, minus 1 over beta jt applied to d log rho. But now in dt. Now jt satisfies a continuity equation. When I apply gt to omega, I don't know how to write it in terms of mu. But if I write it to an exact thing, I know. Yeah, that's nothing but dt mu of log rho. Because that was true for every f, that dt mu of f was j of df. So it's just the continuity equation for the function log rho. And so I get here the integral between 0 and t of minus 1 over beta dt mu applied to log of rho t in dt. But dt mu, so the invariant measure doesn't depend on t. That's somehow really one of these advantages that we took. Independent particles, we don't have to use local equilibria. And so this is just dt rho, let me write like this, log rho in dm beta and in dt. Okay, just because mu was rho m, so dt mu is dt rho m. M doesn't depend on time. My rho, my rho changes from line to line apparently. So now you know. So this guy, let me change color. This guy here is nothing but dt of what? Of rho log rho minus rho, right? Because when you do the derivative of this function, the derivative of this guy is log rho plus 1 minus 1 dt rho. Okay, so that's a total, and then I integrate a total derivative in time, so I get exactly minus 1 over beta, the integral the integral of rho t log rho t minus rho t in the m minus, so I get that this is equal to this guy in the numerator minus the same integral at time 0, just because that's integral in time of total derivative of some function. I'm a bit informal with the regularity of rho, but in reality, everything is OK. You can do it. And you know, this rho t, integral of rho t in dm is 1, integral of rho 0 in dm is 1. So you can, if you want, you can erase this rho t and rho 0 and just remain rho log rho minus rho 0 log 0. So that's exactly, so the scalar product at the end of the day is exactly minus 1 over beta, the integral of rho t log rho t in dm beta plus 1 over beta, the same thing at time 0. Just because the rho was the density of mu, mu is a probability. So even if m was not a probability, that will always be 1. So if you here there is a minus sign, but here there was also a minus sign. Here you have a double product, but here there was a 1/2. The other parts matches. If you put all together, that's exactly minus 1 over beta h of mu t, h beta of mu t. So we got this chain of equalities. Okay?
So S, should I understand S as the symmetric current and R as
Yes, absolutely. S is the symmetric part of the typical current. So if you do it on a Markov chain, that will involve the symmetric part of the rates.
And H would be the quasi-potential.
Exactly. So I think the simplest thing you can do to do this is here, instead of the action function for independent particles, you make a mean field model, interacting mean field model. Here you will get exactly the like the deviation from the car, but how to say, J mu, this, in some sense, this B mu and this Laplacian may depend on mu itself. Yeah, that's the simplest, but in a continuous way. That's the simplest interacting system you can do. And indeed, in that case, H, and then you have different possibilities. If you kind of know the Gibbs measure, you can make this really the quasi-potential with respect to the Gibbs measure. But if you're interested in a finite time limit, like we are doing here, you can do some local Gibbs measure. And there is some error here. But if the interaction is not too singular, it's not hard to control it and to do the same type of computation. OK, if you do this computation for interacting with the mean field interacting potential, as in all these mean field techniques, you can make all the computation up to the Coulomb potential, and the Coulomb potential you cannot cover. So I don't know if you like this interaction in mean field. It's all the techniques have the same barrier. Yeah, I'm here. So OK, so we established this proposition. So let's assume that the initial data is nice. It's not really necessary, but in some situations. But so what we have just checked is Jt is J mu t. So our sort of lift of the Kolmogorov equation. That's the same thing that H mu 0 is bigger or equal, H beta, sorry, bigger or equal than A beta mu t for up to time t, up to t. That's the same thing as Ht of mu j is non-positive. And that's the same thing as this inequality. This is bigger than this, plus 1/2 the integral between 0 and t of I beta of mu t dt, plus 1/2 the integral between 0 and t of jt minus r mu t squared mu t dt. Okay.
It's true that if I minimize that over j, I get jt minus r mu t.
So yeah, so if you do the infimum over all the j such that mu j satisfies the continuity equation of this part, let's say when RT is 0, when RT is 0, so if the system was reversible, that's exactly a gradient system. That's exactly dt mu in this square, in the sense of the metric derivative of the vast extent to space. And that's true on any kind, also in infinite dimension. So that's, and this, while this is h beta of mu, that would be, if you remember this metric gradient of functions, that's exactly the gradient square. That's why here there is beta square in the definition of this, here beta, of the entropy. So this is indeed, if you project it back, so when you take this infimum over the currents, you are projecting back on exact one forms. If you project back this equation, you get the fact that reversible Fokker-Planck equations are a gradient flow of the entropy in the vast extent space, which is a classical result. And what is non-trivial is to get from here these Bakry-Emery conditions. But this is indeed, I don't know. One should start to do all this calculation with curvature and so on. So it's very long. But yes. So cool. What I wanted to say then we want to pass to the limit when b beta converges to beta. We already know that we cannot expect that if the traps are too big, we converge. There's if you remember, I gave you cited the counterexample where you perturb the potential with something which is only C alpha, regularity C alpha. And so we want to know when does it happen. So I will prove a theorem, theorem, which is which is like exercise I did for this class. And this b beta is, so I know how to do these things a bit in the last years. I learned a few of these techniques, and I'm very happy that this example works so smoothly. So what is the idea is that b beta, you will have the convergence of the gradient flow. So x beta to x dot equal to b of x. Okay. If b beta has this form, something that converges uniformly plus 1 over beta, something that converges with one derivative less. Okay. Now, what is one derivative less on gradient beta? It's very clear. You remove the gradient and the function converges, not its gradient. So you converge in C0 and not in something like this. But for R beta is slightly more complicated. So I will just assume that R beta converges to some R uniformly without removing the derivative. So the non-symmetric part, this guy is like nice. Okay. In reality, it's enough that you control it with the symmetric part, as always in this kind of problems. But on V beta, I really want to be nasty because that was our initial motivation. And is that V beta, I assume that is V beta 0 plus 1 over beta V beta 1, where? So where? Where? So V0 beta converges to some V naught in C1. So also, this really converges nicely with also the derivatives, what you would need to pass to the limit in a naive way. But V1 beta is only equicontinuous. Okay, so it's like pre-compact since only the gradient matters here up to constant, we are in a compact space. This is like V1 beta is pre-compact in C0, okay? Along subsequences converges in C0, okay? So I want to prove that this is the sharp case in which you converge. And I think the case where I mentioned some counterexample was the case where V beta was not V0 beta plus 1 over beta, but was some limit, V0, plus 1 over beta to the R, some perturbation U, okay, where this didn't depend on beta. Of course, V naught is the same as there. So you can do as an exercise, if you assume that U is of class CS, so it's older for S in 0, 1, okay, you can check that each potential of this form, okay, can be written in that way, okay, fit in the hypothesis, fits in the hypothesis. if s plus r it's bigger or equal than 1. Okay. So in particular, s plus r exactly equal 1. If you don't do it with these, there are many. If you do in one dimension, there is even some literature this kind of problems. So how much how much R here you need to trap Brownian motion or not. So if S plus R is strictly less than 1, you can make counterexamples. So you see, we make the case S plus R equal 1. I don't know. I wouldn't know how to prove it if not in this way. So while if you have some margin above criticality, you can maybe do more almost everywhere computations. Okay, so if you remember, what do we need to do? Okay, let me make a exercise. If AT, so if mu beta j beta is a sequence in U such that AT of mu beta j beta is even just bounded uniformly in beta, for all beta, then mu beta j beta converges along subsequences. So it's pre-compact, yes? You can extract a compact sequence, subsequences. So here I didn't probably discuss much in which topology, but this means just that mu t of f converges to some mu of f, even as a continuous function of time, and that the integral of jt of omega in dt beta converges to some limit j t of omega dt for every omega. Okay, this is a function of time uniformly in t, and this is in this. It's not hard. It's just I don't prove it. It's very easy. We have this inequality. This is already an a priori bound. The entropy of mu t is bounded. Even if we were not on a compact space, this gives us compactness of mu t if m beta is tight. And this okay. This is also good, but okay. And R mu t is nice. So this tells us that the jt. This squared norm is bounded uniformly in beta because the difference of all this stuff is just A. So this gives you a bound on all. So if A is bounded, since the difference here is A, you have a bound on the entropy, you have a bound on this Fisher form, and you have a bound on the norm of J squared. So you get compactness even in stronger spaces than what I stated. Okay. So let's assume that. This is an exercise on just Prokhorov, Ascoli-Arzela theorem on, we are in a compact space, Ascoli-Arzela theorem on space of probabilities. So, since this converges, to prove, so what we prove in the remaining few minutes is the following. Let's call, so I claim the following, so theorem, let's say, theorem, every limit point mu j of mu beta j beta, which was the pair low current of x beta t solution to okay, x dot is b beta x plus this. That was for the low current, that was the same as jt is this calligraphic j mu t. Okay. So every limit point of this sequence, okay, every limit point mu g of this, which was this, satisfies. I hope that I don't forget any half integral of. So v naught is the limit of of the V beta. Unfortunately, I wrote my hypothesis a bit in the corner here. V beta is V naught plus 1 over beta, a small error, and V naught beta converges to V naught, okay? So we want to say that the error doesn't count. That's what we want to say. So this limit only depends on V naught, okay? D mu t, that's an integral in x, means mu 0 is bigger or equal than V naught d mu at time t plus the integral. So that's these are just integral in x, integral of 1/2 gradient v square in d mu s and in ds between 0 and t. So these are integral in time and space plus 1/2, okay, whatever remained, jt minus r0 mu t. So this is just mu t rt. Maybe I can call it r mu t 0 square in dt. And where r mu t, r mu t 0 of omega was just the limit of the on the skew symmetric part of the current. So this is just mu of r omega, where r is this guy, is the limit of the r betas. Okay, I assume that this goes uniformly. And the same exercise without beta, you can check that this actually means just that j(t) is some, not j mu beta, but j kind of, the limit beta, I don't know, infinity maybe I should call it. J infinity, yeah, maybe let's call this infinity. Beta is infinity. J infinity mu t, where j infinity of omega is just the current for the deterministic dynamical system. It's just mu of b omega. So that's like the law, mu is the law of x dot is b of x, where b is minus the gradient of v plus r. B naught. Okay, so it's like we converge to the inequality corresponding to the Fokker-Planck equation for a deterministic dynamical system. So, okay, so we removed the noise effectively. So if you maybe remember a bit the idea of the techniques that, as we showed in the very first lecture, we just say that, okay, we have this equation. No? This equation, sorry, I forgot the beta here. It means that our pair, mu j, satisfies this inequality. The opposite inequality is like always true. The opposite inequality is A is positive, which is always true. We are saying, no, we satisfy also this inequality. That is, A is non-positive. The action is non-positive. Cool. Then it's enough to pass to the limit inside here. Okay? I forgot, of course, crucial hypothesis, yeah? Provided, so I need that the energy of the initial data converge, provided h beta of mu at time 0 converges to the integral of v0 in the mu 0. Sorry. Now, this you can always do. There always exist initial data like mu 0 beta. I wrote it, yes. So we pass to the the limit in this inequality. This guy converges. It's just hypothesis on the initial data. Actually, we pass to the lim-inf, and then we have okay, proof. It is enough to prove that. So I want to, I have a dynamical problem. Mu and j depends on time, and I want to reduce the problem to a static problem where for things that don't depend on time, that for all mu beta, which are sequences of probabilities without time, there is no underline, such that mu beta converges to mu. So it's enough to prove that, okay, 1. for all mu beta, such that mu beta converges to mu, we have that the lim-inf of h beta of mu beta is bigger or equal than the integral of v0 in the mu. That's the limit of the mu beta. And 2, for each mu beta, the same statement, we have that the lim-inf of I beta of mu beta is bigger or equal than the integral of gradient v0 square in the mu. Okay? So why is it enough? Because then we know indeed. Okay. So let's suppose 1 and 2. Okay, we know that h beta of mu 0 is bigger or equal than h beta of mu. We already made this kind of. I just rewrote that inequality, okay? So sorry for the. That's the inequality all to the right. And then I've just passed to the lim-inf here in the inequality. Lim-inf when beta goes to infinity, where here mu is my mu beta is my solution. Okay, I write that inequality that I know it holds for my solution, my pair mu j. Yeah, maybe I should write it. Sorry, it's better to write more slowly than to be in a hurry and not write anything. So h beta of mu 0 beta is bigger or equal than h beta of mu beta t plus 1/2 I beta mu beta t dt plus j minus r mu t square mu t dt. Okay, that's just the fact that the action that this guy has an action equal to 0. So that's equivalent to this inequality, or action non-positive. So lim-inf of the inequality. Okay, so this goes to integral of v0 in the mu 0. That was hypothesis. That was just the hypothesis on the initial condition. Okay, then suppose that 1 is true. This I know that, so the lim-inf of the sum is bigger than the sum of the lim-inf. So if 1 is true by 1, here I get bigger than v0 in the mu t, where mu is any limit point of mu beta j beta. Okay. Here I have the lim-inf of this integral. Okay, this is positive. By phi2 I can take the lim-inf inside. Now for every t, mu beta t converges to its limit, and again, by 2, here I get integral between 0 and t of gradient v0 square in the mu t in dt. That's 2 plus phi2. Okay, because I know that for every t, my mu beta t converges to some limit point, and this mu t is just this limit point. And the last guy, it's very easy because that's like, okay, let me also pass with the limit inside the integral. This jet is just an integral current, but let me do it just for brevity. That would be just, by definition, this is the sup over all the omega. Here there was a beta. Here there is a beta of jt beta of omega minus r mu t, so here we have a lim-inf of omega minus, with all betas, yes, minus mu beta t of omega square in dt. Okay. Okay, just for so I just exchange with the inequality that I need, the limit and the sup, jt beta of omega. This converges to jt of omega. Okay, it's true that we have compactness in integral sense, but this is indeed an integral. Okay, so jt beta of omega converges to its limit j of omega, jt of omega. I exchange it as the sup. And now here, R mu t, I assumed that R beta converges to R uniformly. So this guy is just mu t of R beta omega. So just this converges weakly, this strongly, this is just weak strong convergence to its formal limit. Sorry if I'm a bit quick here. And this is also omega squared is a smooth function, so this converges quickly. So okay, so that's exactly this supremum over omega is exactly this guy. Okay, so I repeated this technique already maybe 3 times, but it's always, let me be, I was a bit sloppy because it's always the same. You pass to the limit inside an integral inequality and just, I don't know, Fatu or similar tricks allow you to pass to the limit. So we want to prove 1 and 2. So we started a bit late, and maybe I can take a bit more than 1 hour, so maybe we can do a little time, because that's the only kind of computation we do. So we proved these two lemma, okay? Lemma 1 is 1 holds, and lemma 2 will be inequality 2 holds. So just let me comment. Who has heard about the meaning of gamma convergence? Okay, you also heard. Don't be shy, Junior. You know. So just if I have a sequence of function from some space, not important, with space to R, or maybe to R union infinity. Okay. I want to do the leave f beta. I have a sequence of, like there will be h beta and there will be I beta. There is a notion, so usually people can define what's called gamma liminf of f beta of x, okay? Let's call it a mu, at some mu, like in our case. This will be the infimum, by definition. This will be the infimum of the liminf of f beta of mu beta. So okay, you take the infimum of this number, the liminf of f beta of mu beta, but you minimize over all the sequence of mu beta that converges to mu. So you are saying that like the limiting cost of mu is not the cost of, is not the limit of f beta of mu, is the limit of the optimal way of converging to, of the cheapest way of converging to mu. And the gamma lin sup is actually the same thing. It's also a nymph. It's not that because it's lin sup. Everything is a nymph. You want always to minimize. You should think that f beta is like a cost. So just it's exactly the same thing. Just it's the lim sup. Okay? Because I don't know if f beta, when beta becomes bigger and bigger, the values f beta and nothing to do one with the other. Of course, these two guys will be different. But you always try to minimize, okay? There are these two things. And of course, you say that f beta gamma converges if these two things are the same, and you will call that the gamma limit, okay? So here, if you check these definitions, what we are trying to say in 1 and 2 is that the gamma liminf of h beta is bigger or equal, h beta of mu is bigger or equal than v naught in the mu. And a similar gamma liminf of I beta is bigger or equal than gradient of v squared in the mu. Okay. So actually, while for the second I really just need the gamma liminf, and it can be quite tricky to prove the actual gamma limit. For the first h, for h beta, I would really need also to prove the gamma lin sup. Because otherwise, like if I don't have the gamma lin sup, it could happen that there is no sequence for which the initial data converges to, the cost of the initial data converges to this. Okay? So the gamma lin sup tells me that I can produce all the initial data while preparing the initial data at beta. Okay, that's the first thing. So, we want to compute or to bound the gamma liminf of h beta, and then there will be lemma 2 and I beta. Okay? So lemma 2. If I want to write it compactly, is gamma liminf of I beta at mu bigger or equal than the integral of gradient v not square in the mu. So that's what we want to prove, okay? Just as a idea, okay, what would happen if I don't send beta to infinity, but to a finite limit, okay? So the noise stays order 1, I just move the drift. In this case, of course, we don't need, it's enough to have very weak convergence of V, not of its gradient, to have convergence. So let's check not what's the limit of 1 over a, the gamma limit of 1 over h mu beta given m beta, but just let's just first do the limit without dividing by beta, okay? So let's try to have an inequality of who is the gamma, so who is the, okay, let's compute an inequality with the liminf of this. So m beta is given, is e to the minus beta with beta converges, whatever. And mu beta is any sequence converging weakly to some mu, okay? Well, how to make an inequality? It's very simple. That's the liminf of the sup overall function of mu beta of f minus the log of m beta of e to the f. I just exchange here, okay? So, and I get sup over f of mu of f minus the log of, if m beta converges to m e to the f. So I just get, so if m beta converges to some measure m, the gamma liminf of the relative entropy is h, is the relative entropy with respect to the limiting measure. You can do as an exercise also the opposite, that there exists, so to prove that actually the gamma lim sup is h. So if you want, you can say that the relative entropy with respect to, so what I just trying to say, it's very simple to prove the following statement. To prove the following statement that m beta converges to m weakly if and only if the functional relative entropy with respect to m beta gamma converges to relative entropy with respect to the limit m. It's an if and only if. It's very simple to check. We proved just the gamma liminf there, which is the only thing we formally need to prove. But you see, our m beta was e to the minus beta v beta. So if this v beta is like one minima, for instance, only one minimizer, this will be like delta in that minimum, yes? The limit, the weak limit of e to the minus beta v. Typically will be singular. So you see that this entropy, this limit entropy, the cost, if m is, for instance, delta in one point, the relative entropy with respect to a delta function, to a delta measure, takes only two values. 0 if the argument is exactly the delta, and plus infinity otherwise, because you are never absolutely continuous unless you have the delta. So this tells us that this gamma limit is very trivial. It's like if you are doing, I don't know, fn of x is nx plus something smaller. Yeah? If I make the limit of this, okay, it's infinity, or 0 unless x is 0. I'm just not catching the right scale of how this function diverges. I should rather look at this, right? So here we are doing the same. What we are interested in indeed, is not the gamma limit of the entropy, is the gamma limit of the entropy divided by beta. So this gives us, so this first gamma limit is telling us the cost to produce a measure if the limit of m is singular is like always infinity. We are not catching the right scale of the right speed of convergence. So we should divide by beta, okay? That's exactly what interests us, the first non-trivial limit of h beta. Actually, you can prove this statement that this function, or gamma converges to integral of some function in the, okay, in the argument. That's actually is equivalent to say that m beta satisfies large deviation principle with speed beta and rate v. So we prove just, so we just prove in our case that, so lemma 1, so proof of lemma 1. So the proof of lemma 1, again, we just it's very simple because it's still very simple. So let mu beta converge to mu weakly, okay? Again, we just exchange the inf and the limit. We have to get an inequality for lim_inf, then the lim_inf, when beta goes to infinity, of 1 over beta h of mu beta given m beta. That's bigger or equal than the, well, okay, that's the lim_inf of the sup overall function of mu beta of the function divided by beta minus the log of m beta of e of the function. But of course, in this sup, we already call f beta f, okay? Taking the sup over f or beta f is the same. And now I exchange with an inequality the lim_inf and the sup, so I will get the sup overall function f. Beta goes away with beta, mu beta of f, the lim_inf, mu beta of f minus the log, and here we have like the integral of e to the minus beta v beta plus beta f in dx. Okay, and so mu beta is converging weakly, so that's the sup over f of mu of f minus, oh, I forgot 1 over beta. So where does it go? The lim_inf of 1 over beta, the log of e to the beta f minus beta v beta. Our v beta is converging actually uniformly to some limit to v naught, because v beta is the sum of two things that converge uniformly. There is no gradient here of v, that's the point. So this goes to the sup of f minus v naught, sup over x. So it would be enough for this statement for v naught to be lower semi-continuous. Here it's even continuous, so that's actually, I can choose f equal v, yeah, and I get v naught, f equal to v naught, this is 0, and this is v naught in the mu. You can try to make, as an exercise, you can try to prove that for every mu, there exists mu beta such that the opposite inequality is true. Prove that for every mu, there exists mu beta converges to mu, such that the lim_inf of h beta of mu beta is smaller or equal. So it will be an equality by the end of v naught and the mu. So that was easy. And where we see, so we are just saying here that v naught is the large deviation rate of the invariant measure. And where we see really these, where was the hypothesis? So where we see, of course, all the difficulty. So this was v naught beta. This converges in C1 to v naught plus 1 over beta. So this structure of traps we see in the second lemma only. When we want to do the gamma lim_inf, so we want to, so to conclude the proof, we just need to show, we need that the lim_inf of 1 over beta squared, the integral of gradient rho beta square divided by rho beta in dm beta is bigger or equal than the integral of gradient v naught square in the mu if mu beta, which was rho beta and beta, converges weakly to mu. Since I'm a bit late, whoever needs to go, feel free to go. And this is just, we make some slightly more computational proof, not very long in any case. But feel free to go as you wish. You wanted it? No, it's actually simple. Yes, that's okay. This will be lemma 2, and concludes our proofs. Actually, I just do the same. I just exchange sup and limits. So what I want to convince is this: if you remember the initial motivation, okay, it came from some approximation of numerical schemes, but I just want to try to convince you that this technique is very simple. allows you to prove some convergence in law, and then you can try to apply to more involved cases. So it will be actually very simple. If you remember, this guy was actually the S mu square mu. So that was the supremum over all the omegas of m beta of minus 1 over beta d rho omega. That was S mu minus mu of 1/2. Okay, this is 1/2 this guy. 1/2 mu of omega square. That was the definition of our this object here. That's how we got it. So, okay, let's write this thing. This is the integral in the m beta, so it's d vol e to the minus. So here there is beta v beta. V beta is that structure, so there is beta v naught beta minus v1 beta. Okay, because v1 has 1 over beta, and there is a beta here. And then we have minus 1 over beta. Maybe I want to write it as rho beta times minus 1 over beta gradient rho beta omega. Oh, sorry, there is a sup over the omegas. Omega minus 1/2 omega square. And I did right here by rho. Yeah, there was gradient rho. I put a rho here divided by rho, and here there was rho because there was mu. So it's just this. Now, what do you want to do? If you want to pass to the limit, but rho converges weakly, okay, when you integrate functions, but not its gradient. So we would like to integrate the gradient by parts, but the gradient by parts, you would have a gradient of v1. That's a problem, right? Because v1 doesn't have a derivative. But what's the problem? No problem. There is a supremum over omega. We call, so instead of omega, we call it e to the v1 beta omega. And here we get e to the v1 2 v1 beta. Right? Instead of calling it omega, I call it e to the something omega. I multiply my form by a scalar. That's still one form. So that this guy goes away with this guy. And v naught, instead, I know all the whatever I want on v naught. Okay, this guy is a smooth. Probably I want to also call omega beta. Okay, maybe I need to rescale by beta. So that's the sup over all the omega. And now I integrate by parts. So here is the integral in the vol. And when I integrate by parts, yeah, okay, this gradient here, I get, there are some minus. With this minus, it hopefully become probably a plus. Gradient v naught beta. This beta goes away. The rho with the rho goes away. Rho omega, I hope I'm not mistaken, minus, this is a minus, this is a plus, 1 over beta, that's e to the minus beta v0. And here you have this star omega, rho. So I'm doing a bit of a mess, sorry. Rho, and here there is a rho. So I integrated this gradient by part, okay? This rho goes away with this rho. I just put it before for probably no reason. When the gradient goes to with e to the minus beta v, the beta here cancel with this beta, and I get the gradient of v e to the minus beta. And when this gradient goes on omega, that's make the divergence of omega, which is there, okay? This minus goes away with the integration by parts. And then there is minus 1/2 e to the 2v1 beta omega square. So just the rho. I'm happy because v1 beta has never a derivative. And then I take the lim-inf. okay? I just take the lim-inf. So when you take the lim-inf, you can always, the lim-inf is always achieved along some subsequence. You can think it's actually a limit, and on this limit you can take further subsequences, and since v1 beta was equicontinuous up to a constant, okay, up to a non-influent additive constant, you can think that v1 beta converges along a subsequence which was a sub-subsequence of the subsequence making the lim-inf, converges to some v1. So we take all this, we take the lim-inf of just computed on a subsequence where v1 converges, so we get that the lim-inf of I beta of mu beta is bigger or equal than the sup over omega of, I take the lim-inf, maybe not yet. I want to rebuild the mu, no? So how do I write all this stuff? I write it as the integral in the mu beta. So mu beta is e to the minus beta v naught beta minus v1 beta rho beta divol. So what I'm missing, rho is everywhere, very well, but there is e to the v1 beta, yeah, which wasn't there. Minus gradient v null beta omega minus 1/2 so these two here, there is only one of them. It goes away with the one in front, right? So here I have minus gradient v minus omega square e to the v1. I hope it's not 2. I think it's correct. With an inequality is just this lim-inf. And now I'm done, okay? Because this guy converges strongly, this guy converges uniformly, so I just get the sup over omega, and this guy converges weakly. So weak, strong, converge. So that's integral in the mu, where mu was just the weak limit of mu beta, of e to the v1. Just I compute this lim-inf on a subsequence on which v1 converges. Being equicontinuous gives me, on a compact space, up to an additive constant gives me compactness in C. And now, okay, you recall, you call again omega e to the minus v1, the limit omega, and that's exactly, this gives you exactly 1/2 the integral in the mu of the gradient of v naught squared. So it's very simple. You just you just don't need to derive v1. So it's very simple, but it's very sharp at the same time. It gives you. Oh, I erased it, but it even covers this case where you perturb with the Hölder potential and pass to the limit. That's it. So just wanted to get you an interest in this technique, which I found very powerful also to treat infinite dimensional cases, or even finite dimensional, but interacting with particles interacting, and we just deal with the. So what is? Just let me do the following remark. What is interacting non interacting is just this function, this action functional that we considered at of mu and j. Okay, that's the action functional that comes from the large deviations from the pair empirical measure, empirical current of independent particles. Each independent Markov processes, each Markov process solves x dot equal to b beta of x plus the square root of 2 beta w dot. Okay, you make the sum. You make. I think we discussed last time. You have n process like this. You make the empirical measure like this. And you make the empirical current, which it's better to write it always integrated, but it's like omega of xi of s, dxi of s. That's the empirical current, and that's the empirical measure. It's a very, it's meta-mathematical fact that the large deviation rate of the pair empirical measure, empirical current is a relevant object. It's like a dynamical counterpart of thermodynamic functionals. It's a sort of dynamic free energy, okay? That's Claudio wrote many papers on this subject. So even if we take, when we take independent particles, okay, we can even just considering the gamma limit of this action functional, we obtain some interesting convergence results, some stability results. One could do the same for interacting particle systems, where these are, for instance, interacting through a mean field, or even local interactions with. In this case, you would have different expressions for the symmetric and antisymmetric parts of the currents, but so in general, one may require more work, but in some cases, I did something like this with a student. So, but even independent particles, I think, in this scaling gives an interesting convergence result. So it's just like an invitation to look at this kind of techniques, and that's it.